Newton's method is an iterative algorithm for finding the points where a function equals 0, or in other words, we say finding the zeros of a function. And Newton's method, when applied to optimization, gives a procedure for finding the minima or maxima of a function. And Newton's method, well, it was originally formulated, of course, by Newton. Well, maybe not originally. He gets the credit for it, but there were maybe some other people who sort of figured it out before he did. But Newton's method is a second order method, which means that it uses not only the first derivative, not only the gradient, but also the second derivative. So that would be the Hessian in the multivariable case. And this is opposed to, say, for example, gradient descent, which is the classic sort of first order method in which your new point, your xt plus 1 point, is xt minus some step size times the gradient of your function evaluated at xt. So this is a first order type of method, gradient descent. And there's other first order methods also. But here, the only thing that's being used is the gradient, and when we apply Newton's method to optimization, we'll be using the second derivatives also. So it's a second order method. So in this video, we're going to see the intuition behind this application of Newton's method applied to optimization, and we'll derive the multivariable form of this application of Newton's method. So first, let's start out with a little bit of intuition. Now, you may be familiar with Newton's method especially you may be familiar with it in the 1D case. So Newton's method, not applying it to optimization or anything, for finding zeros, so zero finding is your xt plus 1. So we'll think here, at first we'll just think about 1D case. So xt, these are real numbers. And xt plus 1, your new point. You start out with some point, x0, and then you iterate with this formula. Xt plus 1 equals xt minus f of xt divided by the derivative of f at xt. And so what this is doing, if you may remember this sort of thing, what this is doing is you have your function f, maybe it's something like that, and well, actually it should be going through 0, I guess. Something like that. And you're trying to get to a 0 of this function. You're trying to find a point where this crosses the axis here. And if you start out at this, if this is your initial point, then what this does, what this is doing is it's making a linear approximation to the function at that point. If I can draw a straight line, something like this. Making a linear approximation, and then you jump. So you make a linear approximation, and then you find where that approximation is 0. And then that's your new point. So this would be your xt, and this would be your xt plus 1. And by analogy, with this procedure, for finding minima or maxima, so minimizing or maximizing, maybe I should put min or max. Well, what is a min or max? The usual thing you try to do is you try to set the derivative equal to 0, right? You try to set the gradient in higher dimensions, but in the one-dimensional, you try to set the derivative equal to 0 and solve for the critical points. But if you can't do that analytically, then you can use Newton's method. And so Newton's method for optimization, this is for optimization, so that was 0 finding, and for optimization, you're trying to find where the derivative is 0. Here we were trying to find where the function itself was 0, And now we're trying to find where the derivative is 0. So it's just exactly the same, but instead of using f, you use the derivative. So it's just a perfect analogy with the root finding, the 0 finding algorithm. And the picture for this one, for the optimization case, is the following. So let's draw a bigger picture now, so we can sort of see what's going on here. So the picture now, for this case, is that we've got some function, and maybe it's coming along. Let's make it a color. Maybe it's coming along here, and then it straightens out for a while, and maybe it goes up, something like that. So this is our function, and we want to find the minimum. So the minimum is going to be like down here somewhere. And what this does is, let's say we start out here somewhere. Say this is our xt. What this procedure does is it not only does a first order approximation, this was a first order approximation, it actually does a second order approximation. So you approximate this function using a quadratic. That's supposed to be a quadratic. It's supposed to be symmetric. It's supposed to be sort of like x squared, but shifted. And then you minimize that. So if I had drawn it appropriately, the minimum would be right about there. And you take xt plus 1 to be the minimum of this second order approximation. So that's the analogy. So this is the analogy with the 0 finding. It's actually sort of a direct analogy. The analogy with the 0 finding, the original sort of application of Newton's method, extending it to the optimization case. And this is the picture to sort of keep in mind. Now, one thing you may notice here is that, well, if it's the same procedure for minimizing and maximizing, how do we know we're not going to a maximum? And of course, that is a weakness of this, but you can recognize whether what's going on sort of by looking at the second derivative and so on. If it's telling you that the function is convex, then you're in good shape. If it's telling you the function is concave, then you're going the wrong direction. And of course, you can see whether you're increasing or decreasing the function to sort of guide you along the way. And you can shift to one thing people do is shift from Newton's method to gradient descent. If you're going the wrong direction, you can always do gradient descent and just sort of go in the right direction. If you're in it, so that would be like if you're in a situation like this where your approximation is going the wrong way. This would be the approximation. But you can always do gradient descent. Okay, so now that we sort of have the picture in our heads, actually let me draw you one more for the 2D, at least to sort of see what's going on in a little bit higher dimensions. Let's draw one more picture with 2 dimensions rather than just one, to sort of see what's going on, maybe a little bit more generally. So maybe our function looks something like this. I'm just going to draw the level sets of our function here. Maybe something like this. So, and let's say that this is a minimum. So this is in 2 dimensions. And let's say the minimum is right here. Say it has a minimum and that it's there. And say we start out over here. So our initial point is like this guy. Let's make it blue. Well, what we do, or maybe, yeah, that's good. What Newton's method tells us to do is make a second order approximation. And a second order approximation here is going to be, it's going to be a quadratic looking thing. It's not necessarily going to be spherical like I've sort of drawn it, but maybe something like that. And then you minimize that guy. So then you jump to the minimum of that. And that's opposed to the gradient descent, which would just be sort of going in the direction, it would be going in the right direction, but you might not get there as quickly. So that's one major advantage of Newton's method, is that, or second order methods in general over first order methods, is that they can be much faster. Second order can be much faster than first order. Okay, so let's derive this algorithm. Let's derive Newton's method for the multi-dimensional case. Actually, I'm going to run out of time probably in this video. So let me go ahead and stop there, since that's a nice sort of stopping place. And we'll dive into the derivation of it in the next video.